Alrighty, Chapter 1, Introduction to Computers and Programming. Now, I'll give you permission to fall asleep, but if you do, you'll hurt my feelings. And the reason I say that is we're not going to actually have any of this stuff on the final exam. But I think that having a context is important for any discipline, including programming. So, great moments in programming history. At one time, I had kind of a sardonic one of these for the beginning of every chapter, and I need to go back and I need to put them back in. And they were things like when the Mars lander slammed into the planet, and when the Patriot missile shot the wrong thing, all that kind of stuff. Mistakes. Here was one. Back in 1990, AT&T was a huge behemoth, however you say that. They carried 70% of long-distance traffic, and this before everybody had a cell phone. And they experienced a catastrophic failure that disrupted almost all calls nationwide for 7 hours. And unfortunately, I'm old enough to have actually been on the job when that happened. And the problem was a single line of code in an update that they'd pushed to their servers. When I say servers, they're called switches. But a switch to AT&T was just a computer that routed calls. And they were programmed in the C, or the C++ programming language, which is very similar to Java. So after you've taken this class, you'll know what this looks like, what this does, and what's wrong with it. Right now you don't. But I'll point it out. One line of code, or maybe 2 lines of code. The way this works is it was supposed to do something, and then after it did something, it needed to initialize itself. And this break statement meant, okay, we're completely done with this, so go down here. So without this proper initialization, this couldn't work. And this was in a particularly bad piece of code for there to be a mistake. And when the server crashed, or when a switch was unplugged or something like that, when it came back online, it sent a message out to all the other servers, all the other switches saying, I'm back in business. You can route calls to me again. You probably stopped. Hopefully you stopped while I was down. But I'm back up. Please send them to me. And all of the other machines would receive that message, and they'd start sending calls to that machine again. But this code was in the place that responded to those I'm back up signals. So what happened is, you install the update, and on all 1,000, switches nationwide, everything works great. Then one of them crashes, and he comes back up, and he sends a signal out to everybody saying, I'm back. Send me calls. And they all crash, except for the one that just did that. And eventually, one of them reboots, and he sends a signal out, and everything attached to it crashes again. So all the machines were constantly rebooting, crashing, constantly rebooting, crashing, constantly rebooting, and crashing. You can see why phone service was spotty that day. I'd hate to have been the programmer who made that mistake. Boss comes in and yell at you. So what they did is they took the machines offline, and they, installed the earlier version, and they fixed the problem. But, it did take most of the day, and they lost a lot of business that day, along with people who probably decided, well, we're going to go with Sprint, Okay, hardware terminology. All computers have to have these things, right? A keyboard, a mouse, a monitor. Well, nowadays, your phones and stuff don't have keyboards and mice, and the touch screen is the interface. But whatever. There's a CPU inside, which stands for Central Processing Unit. And I'm going to babble just a little bit about how a CPU works. Maybe I should do it over there where there's not as much glare. Anyways, a CPU, Central Processing Unit, had a chunk of silicon with a whole bunch of transistors on it. And basically, all it does is it has a magnifying glass for reading, and it has a pencil for writing. Okay, this is really stupid. It doesn't have those things. But it's got, essentially, conceptually, a paper tape underneath it that holds 1 billion different numbers if it's got a gigabyte of RAM or something like it. And it can go and it can read numbers in it, and it can go and write numbers in memory. And in order to manage that, it's got a couple of things. It's got a timer, which tells it, the timer fires. It tells the CPU, okay, it's time to do the next thing. And nowadays, computers are insanely fast, 2 gigahertz or 3 gigahertz, which means 3 billion times a second. The CPU is doing something. And it's got a place where an opcode or an instruction is filled in. And the opcode is just a list of different commands that a CPU can do. You know, the people who invented the chip get to dictate what the opcodes are. You know, one might be, you know, store something, store the number in the first register. And opcode 2 might be store the specified number in the second register. And a register is just a place where a number can be written on the chip. So we're going to call these things R1, R2, and the opcode. Opcode 3 might be add those two numbers together and store results back in register 1. And command 4 might be write the contents of register 1 to whatever memory is pointed at in register 2. So you have a program written like this. I want you to store 10, opcode 1, 10. The next line might be opcode 2. I want you to store 20. And then the third one. And then the fourth one might say, I want you to write it out. Well, we want to copy this out to address 1000. And then I want you to write out the numbers that were added. So the way it would go would be this. Instruction 1, store something into register 1. Well, I can't read my writing there. Let's see, that's a 10. So now the computer holds a 10 in one place in its memory, in its CPU. And then the next opcode, store a different number into register 2. And computers have, CPUs have lots of registers now so that they can hold lots of bits of data, you know, in their brain simultaneously, not just one or two. And then do opcode 3. Opcode 3 is an add instruction. Add these two numbers together and store the result back in that first register. So it adds 10 and 20. 10 and 20 is 30. Computers are really good at adding. And it writes that back out there. And then we want to put this result on the screen. And we've decided that the way to do that is to write it out to a specific place in memory. So the next instruction, register 2 now contains the value 1000. The next instruction, 4. 4 is a write whatever stored in register 1 to the memory address that's stored in R2. So R1, R2, R2D2. Okay, never mind. So R1, it's got a number 30 in it. And it's going to write this out to RAM at address 1000, wherever that is. And so now we have a 30. So ultimately, that's what the CPU is doing. It's just following a series of numeric instructions. Everything the computer does, fundamentally, is a series of numbers that are being sent to the CPU and then that are being executed one at a time. Now, it'd be a real drag to have to program like this. 110, 220, 3, 2, 104. The oldest of the oldest of the oldest of the programmers in the 40s had to do something like that. But that was actually before signal processing units per se, because transistors hadn't been invented yet. But that's the idea. We get the benefit of writing in a high-level language. A high-level language is an English-like language with words like if and import, include, while. All those things are kind of words that make it easy to understand what the program is supposed to do. So the CPU writes to main memory. Main memory. Why is it called main memory? Well, there are other places in the computer that also have memory. There are things known as caches or caches. Cache is the correct pronunciation, but it's spelled C-A-C-H-E. And in the English language, an E at the end of the word means that the vowel should be long, so I say cache, which is wrong. And a cache is a place near the CPU, or part of the CPU, that is much faster to access. When you're accessing data that's stored on a hard drive, or a flash card that you've installed in your computer, it takes an incredibly long time as far as the computer is concerned in order to pull that data, much less getting it from the internet. You know, you've seen, you access a page on the internet and it spins and spins, and maybe 5-10 seconds later, you get your data. That's an eternity to something that's executing 2 billion times a second. But even a hard drive, even the fastest hard drives, are really slow as far as the computer is concerned. But in order to access that data, in order to pull up your resume and to be able to edit it, it's got to be loaded in the main memory. So it comes up there. Takes a while to load, relatively speaking, because it takes milliseconds to access this, which is a thousandth of a second, whereas this thing is working in billionths of a second. But there's a kind of intermediate memory, so that when the computer is trying to do stuff that is loaded in main memory, it can be loaded in a temporary cache, which is a place that can hold little bits of information that are stored in the main memory, but if it's going to access them a lot, then it puts them in the cache and it can access them much, much more quickly, because even main memory is slow compared to the speed that the CPU is operating at. That's a little bit too much babbling about that. So CPU is the computer's brain, synonym central processing unit, microprocessor. Some people call it a box. That's my CPU. It's not really the CPU, but it is a box that contains the CPU. Other words for it: processor, microprocessor. Other popular CPUs. Well, when this slide was made, the Core 2 Quad by Intel was a popular one. And the Athlon 64, well, I don't know what current processors are now. All the phones use, processors not made by Intel pretty much. They're all from a different company. When a computer performs calculations, it needs to save the intermediate results. And it saves those results in main memory. And it's saved just as a series of zeros and ones, fundamentally. RAM is just, random access memory, is effectively just a long strip where there are little magnetic pieces that can either be blank, uncharged, to represent a 0, or charged to represent a 1. Main memory is also called RAM, often called RAM, random access memory. The memory can be thought of as a series of storage boxes where each storage box contains a piece of information. At its most fundamental, each one is a 0 or a 1, but typically they're talked about in clusters. 8 bits. A bit is a 0 or a 1. It's the smallest bit of information a computer can access. But they're grouped together because we don't want to think about writing 0, 1, 1, 1, 0, 1, 1, 1, 0. We want to talk about numbers, So they group them in bytes. And some clever, punny computer scientist in the 60s or whatever decided that a byte was 8 bits. Somebody else decided that a nibble was half a byte. But, forget that. Byte is 8 bits. And we'll see that again probably later on. So memory is addressed consecutively. If you have memory address 50,000, and say that a letter takes 2 bytes to be stored in this naming scheme, in this convention, then the next one would be stored at 50,002. And the next letter would be stored at 50,004. And the next letter would be stored at 50,006. So, trying to rein back my impulse to babble too much about this stuff. Historical context, programming languages. We're not here to learn to be hardware engineers. Maybe we'll go on to that, but I won't. Instead, we're learning how to be programmers. There are hundreds upon hundreds of programming languages. They fall broadly into 3 categories: machine languages, assembly languages, and high-level languages. Machine language. The machine language is a series of numbers, the opcodes, that control that CPU. It's just numbers. It's pure numbers. Ultimately, it's stored, somewhere as zeros and ones. But you wouldn't want to edit a machine language program in terms of zeros and ones. So these are turned into larger, numbers that humans can understand, 8, 9, 3, 5, 0, 4, whatever. But it's still just a series of numbers. It's customized. It's specified for the specific kind of chip in your computer. If you had a Mac in the 90s, it probably had a chip made by Motorola or IBM, and it ran a completely different machine language, than did the Intel processors. Later on, Apple switched over to using the Intel processors as well, so the underlying machine language was much more similar. Alrighty, so I'm going to take a detour. The ENIAC, which is considered one of the very first general purpose electronic computers. Before that, there still were computers. But an electronic computer, a computing device, is something that runs under instructions stored in its own memory. And that's why your $5 calculator isn't really considered a computer, because you can't give it instructions and keep those instructions in memory and have it run that program or have it run a different one. Instead, it's just a device with some buttons on it and you run it. Now, of course, you can also get programmable calculators now. And then nobody buys those because they all use their phones. So if you look at this, in the 40s, this was state of the art. This was all one computer. And if you bought an Apple Watch, your microwave probably has more processing power than this. It was done with vacuum tubes. Maybe those are the vacuum tubes along the top. I don't know. What's a vacuum tube? It's just a kind of a light bulb. A light bulb is a form of a vacuum tube, although it's filled with an inert gas rather than a complete vacuum. And if it's lit, that means it says 1. If it's not lit, it's a 0. Now we're back to 1s and 0s. So 40s. These were programmed by swapping patch cables, like telephone operators in an old Gene Kelly movie or something like that. And place a call to apartment 3, and have to swap the wires into the patches, Same thing. Imagine having to write a program by doing that. And check it out, he's looking all important and stuff like that, but actually the first programmers of the ENIAC were women. That sounds maybe odd to our ears, but what happened is you had hardware engineers, which were the guys, and then they hired a whole bunch of professors, female professors from MIT and Harvard and stuff like that, to come and be the programmers. And they pretty much had to invent the programming from scratch based on the specifications of the hardware that the hardware engineers gave them. So in the beginning, programmers was a woman's job. Nowadays, well, even in the 80s, when I first took college courses about programming, the distribution was like 60-40 to men to women. And then it diminished for some reason, to where like you usually don't get more than 20% of a programming class being women. I think that's kind of a drag. There's absolutely no reason for it. Here's a computer from the 70s. This one's kind of funny. This one came out before like the Apple II or the Commodore or anything like that, the very early mid-70s. You'd open up Popular Science or Popular Mechanics and you'd see an advertisement in the back for a computer. And you'd order it and it would come with some boards and you're supposed to solder pieces together and you'd build a box like this. And then you'd think, I have a computer. And you'd run it and all it would do would flicker the lights. And if you wanted to write a program, you'd have to set the switches, 0s and 1s, 1 being up and 0 being on. So you might be able to, enter one piece of data by setting some switches and then pressing a switch that was kind of the equivalent of hitting the enter key. And then you'd do another one and do the same thing and do another one and do the same thing. And after you did that 1,000 times, maybe you could actually get the program to run and it would blink the lights. Woohoo, that's our computer. Of course, quickly people came up with expansions that would display some stuff on a screen. And this one's really sophisticated. They've actually hooked up a floppy drive to it. Can't imagine how much that cost back then. Then there were clubs of people, the homebrew computer clubs. And the guy, Steve Wozniak, who invented the Apple II, was one of them. And they take the idea of this, but improve it and make it into something that could be sold. So what's the point? Here's a joke. There are 10 kinds of people in the world. Those who understand binary and those who don't. The reason that's a joke is because 1 0 in binary is the number 2. And here's why. When we count in our brain's operating system, we have 10 fingers. So we're going to call this base 10. We have these digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now when we start counting, we start with 1. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But really, we start counting at 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are our digits. And so if we're going to count, we go 0. I'm going to put spaces in front of these for a reason you'll see. Actually, I'm going to do that. Uh-oh, I've hit the limit. A 9 is the largest digit. What am I supposed to do now? I still want to add one more to it. Well, we know what to do. We know what the next number is. We do it without thinking because we learned it in kindergarten or whatever, right? What's the next number? Yeah, 10. So what happened? This digit, since it exceeded its max, went back to 0, and then a 1 was added to the next column. And the same thing happens like if you're at 1,900, if you're at 199 and you want to add 1 to it, then that one is at its max now. It's exceeded its max. So you set that one back. Whoops, let me do it on the next line. That one gets set back to the lowest, and then the 1 comes over here. Well, whoops, we can't increase a 9 anymore, so that one also becomes a 0, and we carry a 1 further, and then we go to 200. Yeah, there. That's an extraordinarily complicated way of describing what we do, very simply, counting. Base 2 only has 2 digits. Binary. Binary means 2. It's only got 2 digits, 0 or 1. So let's do some counting in binary. I'm going to put up maybe 3 digits. There. I want to add 1 to it. There's no digit past 1. I've already exceeded the maximum that can be stored in that column. So what happens? What do we make that column? Just like we did when we exceeded 9. It becomes a 0, and we have to carry a number. We have to add 1 to the next column. We add 1 again. Now we're going to add another 1 to it. Well, that one's exceeded. So next time that one becomes a 0. Now we're going to increase that one. Whoops, that one's maxed out as well. And there we go. So this is equivalent in our thinking to a 0, to a 1, to a 2, to a 3, to a 4, and so on. There we go. 10 kinds of people in the world, those who understand binary and those who don't. Now you can go home and tell your husband or wife that, and they'll just look at you like you're an idiot. Okay, so anyways, series of numbers, or even if you converted them into something a little bit more understandable, those are not productive, human, comprehensible ways of telling a computer what to do. Yeah. Only the most ultimate of nerds would want to flip switches, like that, in order to enter data into a computer. And machine language is specifically tied to a specific hardware architecture. It's not, quote, portable. Portable means that you could run it on multiple devices. Not only could you run it on your Intel processor, but you could run it on a different computer. You could run it on a Mac, or running a different chip, or on a phone that was running a different chip. So each processor and each operating system requires a different series of zeros and ones being sent to that chip in order to get it to work. So there's one kind of low-level language we've seen. It's machine language. It's just the zeros and the ones, or the numbers that they represent. Assembly. Assembly is when you use English-like abbreviations, and then something comes along and turns these into those opcodes. Load A, jump, move, interrupt. Each one of these is just a different opcode for the processor. So, see an example of Hello World in assembly. I hope I have that out here. Let me go to the contents and see if I have this file. Hello World in many languages. Okay, here's what assembler looks like. If you were learning to program in the 70s, you probably had to learn assembler. And it's just text. That's an opcode, and then there's some more letters, and then there's some more letters, and then there's some more letters. And this is so hard to read that assembler programmers would usually comment every single line of code to indicate what it did. And so, that's still pretty hard to understand, but it's certainly better than just a stream of numbers. And then there was a program called the assembler that went and it translated this text into that stream of numbers and saved it as a file that could then be run by the processor. And all this rigmarole did, is it displayed hello world. Now we just did that. We said hello world, but ours looked, certainly didn't look like that. That's pretty ugly. I wouldn't want to have to do all that to do hello world. Much worse. Well, here's some examples, other examples. If Fortran is a language invented in the 50s. Now this one actually looks pretty good. It says print star hello world, and it's got a little bit of boilerplate, but that's actually pretty comprehensible. It was a big quantum leap for people to be able to stop doing this kind of stuff and to be able to write languages like this. COBOL was another early language. It was arguably the first high-level language, either the first or the second, and it's also still used today. Although most of the COBOL programmers are in their 60s and getting ready to retire. There's a market. Become a COBOL programmer. I don't even know where you can learn it anymore. So, display hello world at line 15, position 10. Okay, so that's English-like. This is a low-level language. That's a really low-level language. And then this is a high-level language, because you can use English-like words in order to tell it what to do. So the advantages of assembly. Why did anybody learn how to program in assembly after higher level languages were invented? It's very fast. It's close to the metal, meaning that you're controlling the processor directly. And if you had an 8-bit Nintendo or a Super Nintendo or a Genesis, they were programmed in assembler, because those machines really did not have much memory to hold large programs. They really did not run that fast. So to eke out all the performance of them, they were written in the most efficient language that was humanly possible to understand. Nowadays, your PlayStations and your Xboxes and stuff like that, the programs are usually written in C++, which looks very similar to Java. Used when extreme optimization is required. We don't teach assembly here. Disadvantages. It's close to the metal. Its advantage is also disadvantage. It's tied to the hardware. You write it for a specific kind of hardware, but if you wrote a Nintendo program, you wouldn't then be able to run it on a Sega. Too many instructions to do a simple task. It took, 8 lines of code in order to do what a single print statement would take. But don't panic. We don't deal with machine language or assembler in this course. We're lucky enough to use a high-level language. Would we rather have to do this? Blah, 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 or would we rather do that? I'd rather do that. There are other languages like Python where you can get away with just a single line of code. We saw that when we did our hello world, we actually had to have a little bit of boilerplate. We had to have the word class in it. But still, broadly speaking, you can get far more done by using a high-level language. So the complexity of programming an assembler or machine language led to the development of high-level languages. Examples: COBOL and Fortran came out in the 60s. 50s, and then in the 60s there were some intermediate languages, and then C was invented like in 1970 or 71, and from that came C++, and from C++ came Java. BASIC was invented in the 70s, and it's still used today as Visual Basic by Microsoft, and so on. So high-level languages, the idea behind a high-level language is that a single statement can accomplish a substantial task. You could open a communication to a file on your disk with a single line of code. Now you probably have to do a little bit of setup, in order to do that, but it's certainly easier than having to do all the stuff that would be required to open that disk drive. If you're going to write something that would open a file on a disk drive in assembler, it would be dozens upon dozens of lines of code. And it contains common mathematical notation, common algebraic notation. Gross pay equals base pay plus overtime. You can express math like that. And it supports higher levels of abstraction. What does that mean? It means that you don't have to worry about it means that you can group things together. You could have one module that reads data in, and you could have another module that processes the data, and you could have another module that writes the data out. So when you're inside that module and writing the code for that module, you're doing kind of a low-level coding. But then when you're done with that, please stop. I am very sorry about that. I have these these little Bluetooth trackers on my wallet and on my keychain, so that if I lose this thing, I can go to the iPad and make it ring. However, there's also a feature on these things where if you press the button long enough, it starts the iPad ringing. And I don't think I was pressing it. I wasn't even sitting down, but it thought I did. So I effectively just butt dialed my laptop, my iPad. All right. We'll learn more about levels of abstraction. Brief timeline. Guess we have this time. 40s were the first invention of digital computers. Digital being electronic computers. I'm going to veer off this for a second and talk about 1800s computers, the first computers. Why did people in the 1800s need computers? Well, they did because, business was starting to deal in large numbers. You owned an empire, and they were trying to tabulate all your taxes, from all the poor people you subjugated. And, the scientists were plotting paths of planets, and, engineers were trying to build steam engines, and they all needed, good ways of doing math, better than just sitting down with a piece of paper. And a lot of math could be automated. And I'll give you an example of automated math. Suppose you had this equation, 2x squared plus 10x plus 3. And we're going to automate that. Oh gosh, I've almost forgotten how to do this. If x is equal to 1, then what is our answer? Well, x squared is also 1, so 2 times x squared is 2 plus 20 plus 3. So 2 plus 20 is 22, 25.
Plus 10.
Yeah, why did I say 20? You know what, I'm going to make this easier. There we go. 2x squared plus 2x plus 2. So for 1, it's 2 plus 2 plus 3 is 7. And if we feed in 2, well, that's 2x squared, that's 2 times 4, which is 8, plus 2x, which is a 4, plus 3. That's 15. Let's pass in a 3. X squared is 9, so that's 18, plus 6, plus 3 is 27. 4, and this is as far as we're going to go. X squared is 16, so double that is 32. 2x is 8, plus 3, so that's 43. I hope. Okay, now let's look at the differences between these. The difference, okay, let's even feed in 0 and see if it fits the pattern. 0 plus 0 plus 3, okay. So the difference between 3 and 7 is 4. The difference between 7 and 15 is 8. The difference between 15 and 27 is 12. The difference between 27 and 43,
16.
Yeah, 16. Now what's the difference between that and that? 4. Difference between that and that? 4. The difference between that and that? 4. So if you have one equation that just consists, of one variable, but with different expressions like that, you can calculate it pretty quickly if you set up a table like this, where you realize that all the answers are going to, you could fill it in this way first. We could write a 4 here, and we're going to say that the difference between 16 and whatever's coming up next is 20, so that this answer was 63. And so if we fed 5 in, supposedly 63 would be the answer. Well, x squared is 25, 50, 60, 63. So check that out. We worked backwards and we got it. You can automate that. You can automate it with wheels. And so one guy named Louis Pascal invented a calculator. Let's see if we can find a picture of it. There we go. You set these little wheels, and then you turn a crank or something, and it would give you an answer in terms of numbers. Then another guy had the bright idea of wanting to make this programmable so that you could instruct it on a series of things to do, not just one calculation. And there was something called the Jacquard loom, which was invented in the 1800s, where it was a loom that wove complicated patterns of textiles based on punch cards, effectively. In this case, the punch cards are wood, not paper. But you'd tell it what to do. And so the guy's name was Charles Babbage. And he tried and just about came up with something where you could feed in data in the form of punch cards, and this is in the 1800s, that would program it what to do, and then you could give it a series of numbers with a second stack of cards, and it would perform a series of calculations. And you saw how we did those series of calculations. What were we doing? We were taking the difference between each one. And so his thing was called the difference engine, his first version of it. You can see it was incredibly complicated. He spent a lot of people's money trying to build this thing. And he just about got it right, but some of his backers bailed, and some of them took the machining used for this, in order to try to recoup the cost. And so ultimately, he didn't get to complete it. But the design of it was sound, and people subsequently have gone on to build them, and they actually do work. So like if you go to some museum that IBM sponsors or whatever, they have a version of it. Not daunted by that unsuccess, how do you like that? Mr. Babbage came out with a different version of it called the analytical engine. The difference engine was not programmable by a series of punch cards. The analytical engine was. And so he worked on this up until the end of his life. And he struck up a friendship with, there was a poet named Lovelace, I forget his first name. No, Byron the poet. Byron's daughter was Ada Lovelace. And Babbage and Lovelace, he'd give her all of his notes on the machine. She was a mathematical wizard. She came up with the programming language that this would have to do. So again, the woman was the first programmer. Kind of cool. Not trying to be down on you guys. I'm just trying to I'm just saying it's kind of interesting that people see technology as a, stereotypically manly thing, and it's not really. I don't know if we need to cover the timeline of these anymore. Anyways, so in the early 50s, people came out with the assemblers that would turn regular, those mnemonic codes, LDA and MOVE and INT and stuff like that, into the machine codes to run the thing. And then after that, the first high-level languages were invented. Those were the ones that supported an English-like syntax. And then in the 60s, something that was a clear forerunner of C was invented. And then in the 70s, the C language was invented, and it was kind of a breakthrough. It was invented by two guys named Kernighan and Ritchie. And it formed the syntax that a vast majority of programming languages nowadays have flowered from. Java. Java was a research project started in 1991 by Sun Microsystems. Now, about 6 or 7 years ago or something like that, Oracle, the database company, bought Sun Microsystems, so they're not around anymore. It was kind of based on the C and the C++ syntax, but it's different. What they wrote it for is they thought that all these devices were going to have computer chips in them, and they needed to be computer programmable. And so they thought, well, we'll write one language that'll run on all of those. And it was actually a good idea. but it didn't turn out being popular for that purpose. So they thought, okay, people are going to need programmable microwaves and refrigerators and especially set-top boxes to control your cable channels and stuff like that. So we'll write one language that'll run on top of all that stuff. So how do you do that? Because we saw that the underlying architecture, the zeros and ones would be very different for each one. The idea behind Java is that you write a high-level language where you issue things like print in order to display something. And then running on the computer is something called a runtime engine. And then underneath that are the actual chips and operating systems for the computer. Now the connection between this and this is very platform specific. But if you write this right, it provides a generic interface so that the high-level language interacts only with the runtime engine. And then it's the runtime engine's responsibility to deal with the operating system. And it's kind of like, some people like to run Nintendo games and old Atari games and stuff like that on their computers, and so they get emulators, emulation software, so that they can play their old Sega games on their computer. And then people will take that emulation software and they'll put it, write a new version of it that runs on the Android phone. Well, only the emulator has to change. The software that was written for the Sega or for the Atari or whatever only exists in the form of a dump of whatever was on the cartridge at the time. Nobody has access to the original source code. But since you have the emulator, you write a different emulator for the different platform, and that's why you could run Sonic the Hedgehog on your black and white iPod at one time. Because somebody wrote an emulator for it. Well, anyways, the runtime engine runs on a whole bunch of different operating systems, a whole bunch of different platforms. And then the high-level language, all it has to do, well, not all it has to do, is it needs to be turned into something that the runtime engine understands. So you write in a high-level language, .java, and then something called the compiler turns that into a slightly lower level language, but not really. It kind of looks like assembler. And I'll go back to that hello world. And it creates a .class file, which contains that assembler type language. And then the runtime engine takes that .class file and turns it all into the zeros and the ones required for that specific hardware. So this is what we're going to do. We're going to write .java, and every time we press that green arrow to run it, the compiler creates a .class file, which gets fed to the runtime engine, and it runs behind the scenes. And all we have to worry about is typing in the Java and hitting the green arrow. And it doesn't matter whether we're using a Mac or a PC or a Linux or a phone or whatever in order to do that. I am almost boring myself. That's hard to do. All right. You've also heard of something called JavaScript, maybe. Well, they've got to be the same thing, right? Java and JavaScript? No. The people who invented JavaScript just took the name Java because it was a popular thing. It had almost nothing to do with Java. It's just that in the 90s, Java got popular, and so the inventors of JavaScript got, we'll tack that onto our name and we'll get a lot of interest. I skipped something. It was originally written for consumer devices like TVs and things like that. Java control your VCR and stuff like that. However, nobody wanted to license Java from Sun. Nobody wanted to pay the fee. Using the language was free, but in order to get a runtime engine for your specific device, you were supposed to pay a licensing fee to Sun. But the sudden popularity of the World Wide Web in the mid-90s gave a new life on it, because you could write the Java runtime engine and run on a computer. And then you could write software that would run both on your Mac or on your Sun or Apollo workstation or on your PC. And it would work the same on all three of those, all four of those, any kind of computer. IBM had their OS/2 operating system. Java ran on all of them. So Microsoft hated that because that meant that you could write software that didn't run on Windows. So Microsoft came out with a version of Java that did a few extra things. Well, I want the version of Java that does a couple more things. I'm a Windows program. I'm going to take advantage of those things that are, that do more. And then, oh, dang, you wanted to run that on a Mac? I'm sorry, you better buy a Windows machine. So Sun sued Microsoft, and Microsoft stopped selling their version of Java, but they invented a very similar language called C++. Excuse me, C#. Anyways, so that's how we came to use Java today. It was originally invented for like appliances, but it was also good for providing functionality for web pages in the early days of the internet, and so it took off from there. JavaScript is a different beast. It runs inside your browser, whereas Java does not run inside your browser. In Java, there's that runtime engine, which is a process that you don't see, but it's out there running. What is a process? It's just a program running on your computer that you don't get to see. You don't get to interact with it. It doesn't have a user interface, but it's there. And on Windows, you can see those processes by launching what's called the Task Manager. You open up a Task Manager, you click Processes, and you see a whole bunch of different things running at the same time. One of them is probably Java. JavaScript doesn't work like that. It gets loaded as part of a web page, and then it runs. The browser interprets it. And for a long time, the different browsers would interpret things differently. Internet Explorer was notorious for being a bad version of JavaScript. It ran it very unreliably, and web designers would pull their hair out trying to get something that would work both on Firefox and on Internet Explorer. But now IBM's browsers are, now Microsoft's browsers are actually pretty good, but their reputation, Alrighty. Programming concepts. I'm just about worn out talking about this stuff, but let's go ahead and hit these ideas. Text-based versus windowed. What's a text-based program? Text-based program is just one that runs in a little shell like this. dir is a text-based program. Now, it's a pretty stupid one. I mean, not stupid. It's a very simple one because all you do is run it and it produces something. But, there are other text-based programs. Primitive word processors. Anything that had like a green screen in a movie where all it was is text. That's a text program. And then you have windowed programs. Windowed programs came, from the 70s, where the invention of the first windowed programs really, that's what we like to use. That's a Windows. That's a window. It takes a different style of programming to get a windowed programming to work, versus text-based. Text-based is simpler, and that's why we concentrate on that in this class. We may write one or two applications that actually use Windows, but it's more complicated because you have to handle more things. Fortunately, they give us a framework that solves having to handle most of these things. But for example, the fact that I tab away from this and then I click this and it comes back and it draws it again, that actually has to be handled by something. It's not just a miracle that it happens. There is some programming code that recognized that this thing was brought back to the front and that it needed to repaint itself. And if I click on a menu, something has to draw the menu choices here and respond to those clicks. Or if I move the window, some code has to handle that. If I kill the program, some code has to handle that. So one of the things in our Hello World in many languages is Hello World for Windows. Here we go. For like the first version of Windows NT back in the 90s. Here we have our Java Hello World program. It's effectively just one line of code, but it's got, 2 more lines of boilerplate in it. Here's the same thing to get a program that would launch a window and then display Hello World in it, written in C++ for a Windows computer back when. You had to write all that. Nowadays it's far easier because the programming languages like Visual Studio and stuff like that come with frameworks, come with libraries that handle all this stuff. And so you go into into Visual Studio, Microsoft's Visual Studio, and you say, I want to write a new application. It's going to run on Windows, and it generates a lot of this stuff for you. And Java's the same way. If you want to put a window up, you don't have to write a million lines of code in order to get a window up. You just include a library with an import statement, and then you make a couple of calls, and the Java runtime engine knows how to make the window. Anyways, so text-based versus Windows. Windowed programming is, people like being able to do all these different things simultaneously. It's a much better way of interacting with the computer, but the programming complexity skyrocketed in order to handle that. And that was brought back down to earth by the creation of libraries, which would handle this stuff for us. And so in Java, there's a lot of different libraries that we use in order to, to encapsulate the functionality of displaying a window or something like that. And so you'll hear the word library a lot. We need to include the something library in order to do this. We have to include a library to write to the disk drive. We have to include a library to do that, to do the other. Event-driven versus batch programs. A batch program is one where you run it, and it goes lickety-split, and it's done. Maybe it takes a long time, but like a payroll program, you have out in some mainframe somewhere, a list of 10,000 welfare recipients, and you run a program, and it goes and it generates 10,000 or payroll welfare checks to send out. That's a batch program. You're not interacting with it. It's just going out, getting data, and doing some results. But then there's event-driven programming. Event-driven, everything you do in a Windows interface is an event. Whoops, I clicked minimize. I brought it back, that kind of stuff. That's the difference between event-driven and batch programming. We don't do batch programming so much, but we really do one level up above batch programs, which is menu-driven programs. A menu-driven program is when you run a program. Am I going to be able to think of an example? Probably not. Where it would display a list of options, and you would pick an option and it would do that, and then you'd get another chance to pick an option and it would do that. So you all have surely seen that kind of program way back when. So it's text oriented, just like that, but it displays a list of choices. And that's pretty much where we're going to be in this class. If you go on to take Java, Advanced Java, you'll do some event-driven programming because we'll be doing more graphical user interface programming. Structured versus object-oriented programming. And interpreted versus compiled. Do I want to talk about those? I may have talked myself out. Yeah, I think I have. But the idea of object-oriented programming. Object-oriented programming is the idea that you can create conceptually, you can break a problem down in such a way as to make it easier to program. So for example, you could create an object that represented a printer, and then in order to use a printer, your program would create that object and then it would issue calls to that object, and that would control the printer. If you're playing a video game and you have a character running around and he has a certain number of hit points and he has a certain number of magic points, he is an object. And so the computer, in order to track that character's progress, instantiates that object. And then if another character joins this party, there are 2 objects. And then another character joins the party, and you have 3 objects. And then you're part of a Warcraft guild, and there's 10,000 people running around. But whatever. So the idea is that they're modeled after the concepts of items in the real world. You'll have a file object that you use in order to write to a file. And you have a scanner object, which is used to get input. We'll use both of those. We'll use a scanner object to get input all the time, except what does it scan? It gets text. not pictures like you think of a scanner that you feed documents into. It gets text. The idea is to make it easier to understand, correct, and modify, so that if there's a problem with the printer, you don't have to go and fix your code. Whoever created the printer object goes and modifies their code. That's the idea roughly behind object-oriented programming. So everything you interact with is an object. This window is an object. That menu is an object. On a graphical user interface like that, everything you see is an object. Same is true on a phone. This is also worth talking about, but I don't want to overload y'all. The difference between interpreted languages and compiled languages. In order for any program to do anything, it ultimately has to be turned into zeros and ones. A compiled language is when the programmer does something that turns the program into zeros and ones. So like you know what a .exe program is. You probably have had to copy a .executable or download one onto your program. That .exe is a compiled program. The programmer created that exe. Or if you download an app onto your iPhone or your Android, that is a compiled program. An interpreted program isn't distributed as zeros and ones. It's distributed as the actual text of the program. Basic programs are distributed like that. It used to be in the 80s when Commodore 64s and Apples and Ataris were popular. There were magazines full of source code, and you could type programs in from that magazine. Well, that was a way of distributing code. You didn't get an executable, you got a magazine full of 1,000 lines of code, and you'd type it in and it wouldn't work because you made a spelling mistake. But whatever. Then, so that's an interpreted language. You type it in and then it runs, or it loads that English-like language. And then it's up to the program to try to turn that into zeros and ones on the spot. So there's something called an interpreter that takes that language, that program, and at that time turns it into the zeros and ones, rather than the programmer shipping out the executable or the app that already is pre-compiled into the zeros and the ones. JavaScript is an interpreted language. It's distributed as an English-like text. Let's see if we can go find some JavaScript in our school's website. We're going to go to rose.edu, and then we're going to right-click on it, and we're going to do View Page Source. And then if we look and we scroll up and down, we look for the word script, we'll see all these references to all these script files. If we click on one of those script files, maybe it'll load it. There we go. Now, boy howdy, I don't want to try to understand that, but it's English words. Now, some maniac has come along and compressed it into some form that's almost unreadable. But at its easiest, JavaScript is not nearly that unreadable. JavaScript examples. Let's go find a JavaScript example. I don't know. Come on. Please give me you. There we go. That looks pretty much like Java in a way. It's just English-like text. When your computer loads a web page, that web page will either include this JavaScript directly or it'll be stored on another web page that's accessible, just like this JavaScript file was when I did view source and I clicked on one of these JS files. The web server gave me this web page, this HTML file, and it also has the JavaScript file. And so your browser downloads both of those. And it's the JavaScript that makes web pages interactive. Before JavaScript, you couldn't have pull-down menus in your web page. Things like Amazon and eBay and D2L would be completely impossible to do in the way that we do them now without JavaScript. JavaScript provides the interactivity. It is an interpreted language. It gets that English-like text, and then it on the spot tries to turn it into zeros and ones. And it used to be that you would run a program and you almost always got some little error down here, that said JavaScript error. Maybe y'all are old enough to remember seeing JavaScript error down in the bottom, corner of your computer. Nowadays, they don't even usually tell you if there's an error in the code. It just tries. It tries to do its best to work around the error. But why could there be an error in the code? Because all it did is it got a text file, that had those commands in it. Maybe there were typos in the text file. That's the advantage of compiled programs. The compiled program doesn't have any typos. The compiler made sure there weren't any typos. And the programmer ran the program before he shipped it out, making sure that there weren't any syntax errors in it. So when you got the executable or the app or whatever, it's supposed to be pretty reliable. They're not going to be, are they really? No, you've seen programs crash and stuff like that. But it's far more reliable than giving somebody a text file and hoping that everything in that text file is typed correctly. So Java is an intermediate thing, or not I won't say intermediate. It's a hybrid of the two ideas. Java takes a English-like .java file, and it compiles it, but it doesn't turn it into zeros and ones. It turns it into the intermediate .class file that I told you about. Did I just write that on the board, or did I type that in somewhere? Yeah. The .class file isn't zeros and ones. It's still almost recognizable as, some kind of with English-like words in it. And then it's up to the Java runtime engine to turn that into the zeros and the ones. So it's the best of both worlds. You write in a high-level language, it's easy for you to understand it. You get to distribute something that's already been compiled, so it's already been tested, and it's like, hopefully no, syntax errors or whatever. So it's more reliable than something that is distributed just as a text document that the program then has to supposedly try to run. I think we're done. And class may actually just about be over anyways. I would ask you to go ahead and finish off the PowerPoint on your own time before Tuesday, and to hit your book and to page through chapter 1. Just to kind of get the broad concepts. Like I said, you're not going to be quizzed on it, but don't just totally blow it off. Go ahead and read chapter 1. And it'll be covering these concepts in a slightly different way. And then when you come in on Tuesday, we'll actually do some lecturing. I mean, not lecturing, we'll actually do some programming. All right, hope this is somewhat interesting. Some people think it's interesting, some people wish that they hadn't come to class today. But all right, so I will see you all on Tuesday.
Have a good weekend.
Oh, you too. Oh, and I'm going to make a video that shows how to install Java on your home computer. So look for that. I'll send some email out about it, or I'll text y'all both.
Since I don't know when they will actually get my school stuff, like accounts enabled, I'm going to just text you my other email address.
Okay, cool.
For the time being.
That'll work.
Yeah,
I upload my videos to YouTube, so you don't have to access D2L in order to get them. So I'll
For the PowerPoint
email them. Yeah.
as well.
Okay, that's cool.
That's the habit. No, I did that.
Well, made me think that I do that, because that's what I
Yeah.
usually do at work too.
Yeah, I was like, oh, it's time for walking. Have a good weekend.
You too.
All right, we'll see you on Tuesday.
See you Tuesday.
Maybe we'll be able to get in.
I bet you will by then.
What class was that?
That was Java.
Oh.
Although what you're seeing on the screen was examples of horrible things other than Java. I was trying to compare. Aren't you glad you don't have to do this? Like the olden days when people had to write programs in assembly.
Yesterday, I had texted you about getting into your script programming online class.
Yeah, I didn't get a response yet. I'll rattle cages tomorrow to make sure that that happens.
Okay, well, because I talked to Johnson today.
Oh, you did?
And he said, as long as you send him an email saying add me with my student name and number,
Okay.
he can get it to happen.
Now I did that.
Oh, okay.
So
Well,
I'll do it again to make absolutely sure he gets it, okay?
Oh, okay.